Extension module. Let's take a look at another example. Here, we can see the difference in the speed of an operation being performed on floating point values versus integer values. And here I'm going to do the dot product again, but I'm going to do the dot product on floating point values. I'll do the dot product on integer values, and I'll do the dot product on very large integer values. And another thing we can see here is, oh, when I do the dot product on floating point values, it seems to be fast in integer values. I think I had a performance result previously that showed the integer operations were faster than the floating point operations. You can see that's not a particularly durable result. That would lead me in a direction that would be leading me astray. But here we can see something quite significant. Irrespective of how I set up this example and irrespective of how I lay out these elements in memory, it's probably the case that the big integer operation will be a margin slower than the floating point operation, because necessarily we know the following. These integers are greater than the size of one Python S digit. You may know that a Python integer is actually a contiguous C array of 32-bit digits. Here, the 64-bit is to kind of lead you to think about things like 64-bit integers, but I suspect that if I were to make these values anywhere from 32 to 33 bits in size, we'd see that same performance degradation. It's not because we're hitting the bounds of a 64-bit integer, because Python doesn't work with 64-bit integers. Well, at least it doesn't work in terms of how it stores them. Here, what we can see is the need for software support in order to support automatic promotion, that is to say, to avoid overflow and underflow issues, gives us performance degradation, which is to say that we're getting a significant performance degradation from the correctness of this code. Because if we were to do the exact same example with the exact same original values in NumPy, it would be much faster. But the answer would have rolled over, and the answers would have been wrong. Here we can again see a durable result of our performance analysis. It is the case that when we work with Python integers, we do have some safety from these things automatically promoting, but we lose some speed from that. And when we choose to use other tools like NumPy, we have to be very aware of what we're trading off for that. If we did the exact same example with the decimal module, we would again see a significant performance degradation because that requires even more software support. But we might really ask ourselves, is this performance degradation something that is worth the correctness that was added to our code? Often the case is that when you're dealing with IEEE 754 64-bit floating point types, the imprecision and inexactness that you get requires values that are small enough or large enough that the decimal module might not really add that much to your life. And as a consequence, you might say, well, maybe in our case, we can deal with the noise that's added by the inexactness and imprecision of IEEE 754. But in other cases, you might say, you know what, that performance degradation is something that we just have to swallow because we need the correctness for our code. Here, I want to time for you just a Python function call. And I want to show you that Python function calls are relatively slow. If we take a look at the speed of a Python function call, we can also see something quite interesting. We can see that the Python function call used to be really slow, 61 nanoseconds for just a function, and the function doesn't even do anything. Look at Python 2. Look at how long it takes to call a function in Python 2. Python 3 is doing a little bit better, but notice Python 3.11 and Python 3.12 are doing way better. It is genuinely the case that the work that's been done in recent versions of Python, 3.11, 3.12, and so on, are significantly speeding up Python code, even for people who do most of their work using NumPy and Pandas. Because speeding up Python function calls by themselves is generally valuable to code overall. Reducing the number of function calls that you make in your code is something where you're thinking, is there really an easy way for me to do this? Is this really valuable for me to do? Is it really valuable for me to avoid calling len in a tight loop to avoid the pain of that function call instead of doing something like this and first computing it ahead of time? This could have some correctness issues if this loop later did something like appended to this list that we're working with. But I guess in this case, those might be very visible very visible change that might lead us to say, oh, we can't predetermine the size of the structure. Whatever the case may be, I don't know that that's a change that I would make, but when I see the performance of just a function call, it is a little bit worrying. Well, the faster Python work is speeding things up, and in my view, the goal of that work is not to speed up Python to make Python fast, but instead to sand down the edges where we might get perverse incentives to write code that is simply worse, less readable, less extensible, more prone to error, simply because it happens to be slower to write the correct code than to write the code that is potentially incorrect or open to later bugs, but is faster. Here's a similar example. Here's a function with 4 arguments. Let's see how long it takes to call this function with 4 arguments, about 38 nanoseconds. Let's pass those arguments by keyword. Wow, 64 nanoseconds. It is way slower to pass arguments by keyword. Is it really the case that we want to go and rewrite all of our function calls to use only positional arguments? I don't think so, because the worsened readability will affect all of us. This is where I think things like the faster Python effort can really have some impact. I don't think necessarily the goal of that project should be to make this as fast as it is in C. That might not be even possible. But instead, what I think should be the case is we should make it so that the slowness that we get from writing the better version of this code, the more readable version of this code, isn't as severe as the speed that we get from writing the worst version of the code. Now, for completeness sake, I'll show you what happens when we mix positional and keyword arguments. And you can see once we introduce one keyword argument, we're going down a path where the code is going to have to parse those keyword arguments. It's going to have to build a dictionary, and then it's going to have to unpack that dictionary at some point. And so I think that if we really wanted to take this performance analysis to heart, we would eliminate all use of keyword arguments everywhere, which definitely will lead to correctness issues later on. For example, the author of this code might have made these positional only arguments in order to allow themselves to reorder them at some later point, or in order to force you to do something. And the introduction of making these positional only arguments will break your code, or the reordering of those, assuming that people only ever pass these by keyword, will break your code. Here, just for completeness sake, I'll show you what the time of using star_args unpacking is. And again, we get the same results. Any one of these mechanics that we rely on every day, they're actually not very fast. Here, this is star_args, this is star_kwargs. And here you can see a mix of star_args and star_kwargs. They're all much slower than not using them at all. But I really don't think that that's a guidance for what we should actually do in our work. Here, we can see another reason why Python is slow. If we compare the speed of this code, which has a custom class and calls the underscore method, the data model method, add on it, we can see that this is going to be slower than the version that does the same thing for, say, integers. If we compare this is 7 nanoseconds. Oh, let's do that one more time. If we can compare this, this is 67 microseconds per loop. But if we do the same thing with just integers, it's 4 microseconds per loop. Well, here, is the guidance to only ever use built-in types in Python? I don't think so. I think the guidance is to be aware that Python has this dynamic dispatch. Every time it's going through this loop, it's going to have to figure out what add operation. And there's actually quite a few of these. It'll have to determine whether it wants to use an add, whether it wants to use an radd. It'll have to look at the type of both things. It'll have to find the most common base type for these in order to try and dispatch those. And there's quite a bit of steps for determining this dispatch. The steps for determining the dispatch in this case will be less, and we may spot some performance improvements made in recent versions of Python, where you can see a good margin between Python 3.10 and 3.12. Likely this is the cause of specialization, where Python is identifying that this is an operation done on just integers, and as a consequence, it's specializing the operations and it's avoiding some of the dynamic dispatch. Being aware of dynamic dispatch, I think, is very valuable in general. Here, in this case, we're going to measure what happens when we do this operation with mixed arithmetic types, with integers, floats, and complex numbers. And here, we just have 3,000 integers, floats, and complex numbers. And you can see it's 116 microseconds per loop. If all I do is swap the order of these two loops, let's turn these both into Python 3 only. all I do is swap the order of these two loops so that the integers are next to each other versus interleaved with the floats and the complex numbers, we'll see a significant speed up. And the reason we'll see a significant speed up is, well, you can think that there's some branch misprediction happening as a consequence of that dynamic dispatch. When the integers are next to each other, even in the absence of some specialization instruction, where we know those specialization instructions won't exist on versions of Python like Python 3.8, it's the case that there are some branches that are being taken to determine what do I actually do. And if they're next to each other, well, your CPU can guess, okay, take this branch. Well, take the branch again. We've taken the branch twice. Let's just keep taking it. It can guess which side of the branch to take, and it'll be largely right. But if we interleave these values, there may be some misprediction because it'll say, oh, there's an integer. Oh, no, now it's a float. Oh, now it's a complex number. Oh, now it's an integer. And we're going to confuse our branch predictor. Is there something that we can do about this? No, other than depart from pure Python code. But it's definitely the case that this gives us some guidance on a durable difference between these. It would be the case where we'd anticipate seeing this slowdown, even in the presence of specialization operations, just because fundamentally switching between the different modes of addition, from the floating point to the integer to the complex number addition, is going to be expensive no matter what. So having looked at all of these little micro benchmarks, you might wonder, what do we actually do in practice? How do we write faster Python code? And how do we take these and determine what we should actually do for our work? I want to show you a live coded example where I'll show you my approach for writing fast Python code. Let's say in our example, we want to work on some data operation. And we want to work on a data operation involving a number of different data files, each containing some data set that we want to operate on. So I'll just set up the problem very quickly by first creating some data sets. Now, for this, I'll make use of my Python that has NumPy available, because I really think that when we're talking about performance in Python, we cannot avoid talking about NumPy or pandas if we're doing data analysis, or our own custom equivalents of NumPy and pandas, our own home authored restricted computation domains if we're not doing that. For example, to just give you a sense of what this might be, let's say we were doing a video game. And as part of that video game, we wanted to have some physics operations in order to see where the elements of that video game might bounce into each other and bounce off of each other. It's generally the case that if we were to implement those physics in pure Python, they will be slow. Is it the case that if we implement those physics in NumPy, it'll be faster? Maybe, probably a little bit faster, but it'll be very clumsy. But we might find some C extension module, for example, Chipmunk, where we can drop down into a C level and do these operations very quickly and then bring those back up into the Python level. For the time that we have, I can't show you the creation of a restricted computation domain, a custom one in Python, but we can use NumPy and pandas as a placeholder for something that is more general than just a data analysis case. So here's what I'll do. Let's create some entities in a pandas series. And I'm going to do this, actually I'll create some categories. I'll show you a very common problem. So let's create some categories in this pandas series. Let me create a random number generator for this. And I'm going to do this across a number of different files. So let me do this for a number of different files. Let's also get pathlib. It is not uncommon that when I write my Python code, I'll make use of almost everything I can in the Python standard library, and I won't really worry about the import times of things from the Python standard library. The reason for that is, in general, when I take a look at what is already imported, when I just run an empty Python program, here I'll just import sys, and I'll show you just the modules that are available. In an empty Python program, we'll see that I'm already paying the cost of importing a bunch of stuff. Here, I've already paid the cost of running the code in all of these modules. And so adding more imports, not really going to make a huge difference for me. In fact, if I do this with the -S flag, the site flag, you can see it trims this down. It doesn't include things like matplotlib or my YAML library, because it's going to exclude all those .pth files that'll be in third-party modules that I've installed, but still there's quite a bit that is already imported just to get this empty interpreter to work. And so for the most part, I don't really stress about the import times of things from the Python standard library, although I might stress about the import times of things from outside the Python standard library. I'll show you what I mean. Let me import networkx, just show you how long it takes to import networkx. Let's do the same operation with just a pass. So it took me 0.13 seconds to just import networkx versus 0.02 seconds of wall clock time to do nothing in this program. There are certain modules out there, third-party modules, that are just very, very expensive to import. NetworkX is one of them. Pandas, NumPy, and Matplotlib are also cases of relatively slow modules to import. You can see Pandas is even worse. Historically, NetworkX used to be the worst of these, but you can see Pandas now has gotten pretty bad. It's almost a half of a second. For the most part, I'm going to write my Python programs so that either, if they're short-lived, they're still doing enough work that the noise of just the imports, which here you can see if I imported all of these, could be up to a second of time. Let's really see this. NetworkX, Pandas, and NumPy. This could be, here this is about a half second of time. If we add in, trying to think of something really slow. Maybe Xarray might be slow enough for me to add in here. But I'm now getting closer and closer to 3/4 of a second, maybe even a full second of time. Well, I'm probably not going to write a Python program where I'm sensitive to that 1 second. If I'm using these modules, I'm doing enough data analysis that the whole program runtime might be a minute, in which case 1 second is really noise here. And so generally, I'm careful about my third-party module imports. I'm not that careful about my standard library imports. And generally, part of the premise of using Python in the first place is the script that I'm writing is going to run for enough time that this is just water, this is just thermal noise, this is just noise that I don't have to worry about. Here, I'm going to create some categories. So let's create quite a bit of data by creating, say, 100,000 categories of length 12. And we've done this enough times that we know this from heart. So there we go. So those are all of our categories. We'll create a data set, and we'll create this data set by indexing on those categories. And we'll create, let's actually make this 20,000 categories and 100,000 data elements. So here we go. And here we can see a common problem of something that we know is slow in Python, not as a consequence of the slowness of NumPy or Pandas, but as a consequence of slowness of Python. That is to say, grouped weighted summary statistics on high cardinality groupings. So here, let me get a value for these indexes. So here we'll just do normally distributed values. And there we go. So here we have a series with many repeated values. If I do a group by its index and I do a count, you'll see that there's a lot of different categories, not that many elements per category. And the operation that I'm going to think of doing is maybe I'll do a grouped weighted operation, because that'll definitely be slow, even in the face of fast code coming from NumPy and Pandas. So here we'll get the values and the weights. So here's our value, and here's our weight. And the weight can just be a integer from 0 to 10. Actually, make it from, let's not have 0 weights. So there we go. Now, what we'll do, let's make that integers, is we'll do a bunch of these data files to represent an actual case where we'll have to use pure Python to load each of these data files. So I'll create 100 of these files. And here we'll say, we'll call this data x dot, and we'll save these as pickle files because I don't really care about reconstituting all the structure of this thing. So here we go. And we'll write this out. And we'll write it out to our data directory. And of course, if this thing doesn't exist, we'll create it. And if we need to create parent directories along the way, we'll create that as well. So here we go. We now have a bunch of data files in a data directory that we have written out, and this constitutes about 100 times 100,000, so about 10 million rows of data. Here's the Python program that we'll write.